Hi all, this is Mr. Yeager for chemistry. We are looking at the formulas now we're going to be using in the solutions unit. Let me get that out of the way. Okay. Now, these formulas, I've seen students really struggle in this unit with getting to these formulas because we've just finished stoichiometry and they think it's a lot of steps and everything. There are way less steps involved with these formulas, so we need to take them for what they are and not make them more. Is there some stoichiometry? Yes, we see that in the top search bar up there, not search bar, but like you see on the top of my webpage there where it says solution stoichiometry. We will use a little bit of that this unit. But these are very much two variable solve for the third variable formulas, okay, that we should be able to manage very, very nicely. Now, yes, there are kind of a lot, but we should be seeing those just fine, okay? So, there are lots of different ways that we measure the concentration of a solution. Okay, you probably have seen that probably haven't seen a lot of them at stores. You probably maybe see percent volume when you buy maybe like isopropyl alcohol or something like that, like rubbing alcohol. Those types of things, you'll say like 70% volume alcohol. Same thing with like hydrogen peroxide. So a lot of things that you help, obviously, clean wounds and stuff like that. But in a laboratory, we use other forms of concentration too, and again, pharmacists would definitely be using this, drug makers and things like that, in terms of creating the appropriate medicines for people, okay, trying to get them correct. So, two terms real fast. You heard me say concentrated. Concentration, I didn't exactly use that term last video when I was talking about all the solutions. Something that is concentrated is basically saying that we have a lot of stuff in it. Something that is diluted is something that has more solvent. I don't want to say has more solvent, but the particles, the solute particles, are more spread out, okay? Because we're going to talk about how to dilute substances as well today, because that's part of the math, all right? So that's what I mean by concentration. Concentration, the term basically means how much stuff, how much solute is in the solution itself. So, we have three formulas that we are not going to use that much. I mean, you might have one problem on the test, two problems on the test, and then move on. It might be in like your multiple choice section or something. But we have percent mass and percent volume. I'm looking at those two first. There is mole fraction as well. We barely use that one at all. I'm probably more just mentioning what it is rather than ever testing on it. So percent mass is where you do mass of the solute divided by the mass of the solution times 100. Percent volume, volume of solute divided by volume of solution times 100. So very similar formulas there. The only thing I would just make sure is that you have the same units for the solute and the solution. I've seen that where people could get confused where I give you grams of solute but then kilograms of solution. They need to be the same unit before you divide them, okay? Because they obviously, technically, we cancel the units out, so they have to exactly match. Then there's this mole fraction thing. That is used in particular calculations for something called osmotic pressure, which we actually will mention, but we're not going to calculate. We don't really worry about that in this level of course, even it being at the honors level too. So let's just look at these formulas real fast so that you can go through them and be like, okay, I can see what you're doing with it. What is the mass percent of a solution made by dissolving 0.49 grams of potassium sulfate in 12.7 grams of water? Again, I can see people going, do I need to change the moles? Should I do this? Should I do this? No, no, no. Okay, all you got to do is 0.49 grams of the solute. Okay, because again, I'll write it over here. Percent mass is mass of the solute. Oops, S-O-L-U-T-E. Divided by the mass of the solution. Okay, times 100. Okay, so 0.49 grams of solute, okay? But then I need to add the two chemicals together. So that might be where you're kind of going, wait, should I see people probably just put 12.7 down here. 12.7 is just the solvent. So I need to add the two of them together. 12.7 plus 0.49 is 13.19 grams times 100. This will equal 0.49 divided by 13.19 times 100, 3.72%. Again, using our sig figs, 3.72% or something close to that, okay? So that would be your percent by mass. So I guess, the only thing to pay attention to is if I'm talking about the solution, this is solute plus solvent. So make sure you don't forget that part, okay? But a pretty straightforward calculation in the end. You got it? You do have to recognize what's the solute and what's the solvent. We never do percent mass usually of the solvent. It's just of how much of what we added in there that we're interested in and what percentage of the whole solution is it. In this case, 3.72%. If I do a volume one, okay, I'm making a solution made by dissolving 110 milliliters of ethanol into 15 milliliters of water, okay? And again, some people might go, well, which one's the solute, which one's the solvent? It says we are dissolving the ethanol in the water. It is always solute in solvent. So we do have to use the context of the problem to understand this as well. This might be kind of surprising going, oh my gosh, like, is it really dissolving in 15 milliliters? Maybe not, but that's how we're approaching this. So 110 milliliters of ethanol divided by 125 milliliters of solution times 100, just double checking again, is 88.0%. Okay, that would be our answer to that second one right there. The third one I'm just doing just so that we can see that we might have to rearrange it. It says that the volume percent is 2% and the volume of solution is 250. What's the volume of the solvent? Or sorry, solute. So volume of the solute would be on top divided by 250. Technically times 100 equals 2%. As I always tell my students, just immediately change that percentage into a decimal. So this is 0.02 and then 250 times 0.02 is 5 milliliters. The volume of solvent is 5 milliliters in the end. All right? So those are your percent volume, percent mass calculations. Again, hopefully fairly straightforward. Just make sure you do read the problem for context to determine whether you have to add the two, like, are they giving you the total solution like this one is? It says this is the total solution volume. Or like the other two you saw where I have to add the solute and solvent together in the end. All right, that would be the most common mistake. All right, mole fraction, I'm just showing this again. I don't have any intention of having this on a test or anything, but how would we use it? Moles of solute over moles of solution. 5 moles of NaOH is dissolved in 10 moles of water. What's the mole fraction of NaOH? It would be 5 divided by 15. I would add up 5 and 10. All right, no, sorry, we're not multiplying by 100. This is not a percentage. And so the mole fraction is 0.33, okay, or 1/3. I know it says mole fraction. We usually still change it into a decimal, okay? So that's mole fraction. All right, let's head back. The bigger, more important formulas are going to be molarity and molality. And I know it's like, oh my gosh, what the heck, okay? Why are they named so close together, okay? Molarity, which is big M, that's probably the more important one, is moles of solute over volume of solution. So we do still need to do a mole calculation. We're still going to have to deal with molar mass. Okay. Sorry, just trying to organize something here. So moles of solute over volume of solution. The volume of solution must be in liters. And that'll be something, again, we got to pay attention to. We are going to be doing plenty of milliliter to liter, liter conversions. Remember, there's 1,000 milliliters in 1 liter. Okay, so we're going to have to either divide, we're going to probably have to divide that milliliters by 1,000, change it into most likely a decimal, okay, or at least make it a lot smaller. But moles of solute divided by volume of solution. M, big M, is the unit that follows that number, the molarity. Okay, that's the unit for molarity. Then we have molality. Molality, which is little m, is moles of solute over mass of solvent. So you actually you don't do the whole solution, you're looking at just how much solvent is there. And the mass has to be in kilograms. That one can be a little confusing because you might see that you're going to be given grams of solute and grams of solvent. You need to make sure you, again, read for context and know which one to convert to what. Okay? But these are, the reason we have these, while molarity will definitely be the one that's more popular out of the two of them, we do have a very specific use for molality, and that's why we need to make sure we are prepared for it. Okay? And a use that obviously is very relevant to what we do, especially in winter. Okay? So, the big things with these formulas, I always just tell students, I mean, because I have students that for whatever reason, they're like, these are so difficult, okay, after they do so well in stoichiometry, is I tell students to write out the formula, okay, write out big M moles and liters, or little m moles and kilograms. And then read the problem and figure out what you have to do. If you're given grams of solute, let's convert it to moles first. If you're given milliliters, change it to liters, and then solve. Or, in some problems, guess what? I'm going to give you the molarity and maybe the volume, and then I want you to go back and solve for grams. So what would I do? If I give you molarity in liters, I solve for moles, and then I convert back to grams using the molar mass. Same exact idea with molality, all right? The way I try to have people where they're like, how do you remember molarity, molarity? You know, I don't remember which one's the kilograms, which one's the liters, is I say molality already has the extra L, so it can't be liters, okay? Molarity wants a second L, and its second L is with the liters from the unit. I know it's not a great example, but hey, it's something, right? All right, so let's do a couple examples with this. Okay, you have 3.5 liters of solution that contains 90 grams of sodium chloride. What is the molarity of that solution? So again, I tell students, write out molarity, moles over liters. I'm given the volume of solution, so 3.50. I'm given grams. I can't plug in grams in this, so I need to change 90 grams of NaCl to moles, and then I can plug it on in. Well, NaCl is around 58.45 grams, I believe. 58.45, yep, per 1 mole. All right, I divide those two things, 90 divided by 58.45, and that is 1.5. I'm going to keep some digits. Again, I don't round until the very end. 1.537397, okay? I can then divide that by 3.5, and now I get my molarity. My molarity, 3 sig figs, is 0.440, because it actually is 0.4399, so I got to round it. 0.440 molarity. We sometimes shorten it to just molar. So this is a 0.440 molar solution of sodium chloride. All right? So again, write the formula out. Let's do another one here. You can see it says you have 800 milliliters of 0.5 molar HCl solution. How many moles of HCl does the solution need? So this is nice because I only need to get to moles. I don't need to convert back to grams. But people, again, my students will say, I'm confused where things go. Let's write it all now. Well, you're given the 0.5 big M. So 0.5 big M. 800 milliliters, I need to convert to liters. I divide by 1,000. I mean, this should be something we do in your head. You don't have to show me how to convert units. You should be able to just do it. And then I want to solve for moles. So I'm going to just multiply by 0.8. 0.8 times 0.5. Guess what? It would be 0.4 moles of HCl. If I wanted to find grams of HCl, I would convert it back to grams with molar mass. So that is a molarity type problem. And again, it should take some time. We should practice this quite a bit to get used to it. Molality, I'm just showing you one problem for now because we're going to do a lot more when we do colligative properties. A solution was prepared by dissolving 17.1 grams of sucrose, C12H22O11, and 125 grams of water. Find the molal concentration of this solution. So molality, which we can shorten to molal, okay, is moles over kilograms. Which one is which? I am dissolving the 17.1 grams of sucrose. So that should be up top. I need to change 17.1 grams to moles. And the water is my solvent. So I need to change 125 grams to kilograms. So that's 0.125, 17.1 grams, 1 mole. Let me look at my work here real fast. For sucrose, where are you? It's 342 grams per mole. So if I do the calculation for that, 17.1 divided by 342 is 0.05 moles divided by 0.125. The molality is 0.4, technically 00 molal. We need 3 sig figs there. Okay, so 0.400 molal. We go all the way back to the original number. I can't just use this, even though this is what it comes out as in my calculator. I have to use the sig figs in the very beginning. So again, this is 0.400 molal with little m. Okay, and you can see I'm just writing that little m or big M after it. All right, so those are some of the important, and what is this measuring? This is measuring the concentration of solutes in the solution. Okay, so we got one more thing. Look at that guy doing the figure skateboard. Okay, we have one more formula, dilutions. Okay, and like I say, we talked about this. I'm sure you've had a watered down soda, juice, you know, or something else where you're like, oh my gosh, what happened? And it's because it got diluted. All right. If we have something diluted, the solute is spread out more. It's not like I've lost any solute, that you still have all of that, those Coke flavors in there, but it's so much more spread out that it doesn't taste as good anymore. So again, a lot of times when we purchase chemicals for the labs, and I'm sorry, I'm kind of changing stories here. Usually this is important to understand how to do dilutions because when we purchase chemicals, we get very concentrated chemicals. And that's because I can then pour a little bit in with a lot of water and all of a sudden have a lot more of that quote unquote volume of chemical at a lower concentration. All right, so that's why we are interested in this dilution formula. The formula is M1V1 equals M2V2. All right, where M is molarity, V is volume. Okay, that I feel like sometimes is confusing. Okay, so sometimes while that is like the official way, you'd see it in online or on textbook, I like to write it as MCVC equals MDVD, where C stands for concentrated solution, D stands for diluted solution. And so what I have there is basically I'm talking about the idea of, hey, I want, like, in the problem, when you read the context of the problem, you will be able to tell what is your concentrated volume and molarity, what is your diluted volume and molarity. When I do M1, M2, people sometimes get confused and they're like, which one should I use for M1, which one should I use for M2? Wait, does V2, like, does this volume match for M1 or M2? How do I know which one? So from a contextual standpoint, read it for which is the concentrated solution and which is the diluted solution, and pair up the molarity and volume. For this part, as it says here, you can use any volume unit you want as long as it's consistent on both sides. Okay? So if the problem does give you milliliters and it says how much volume is V2, you can solve for it in milliliters. The only thing we got to be careful of is if like this is in liters and then this is in milliliters for some reason, you got to convert one to the other. Like we have to have them be the same before we combine everything. Okay? So let's show a problem here. Okay? A chemist starts with a 50 milliliter solution of 0.4 molarity NaCl and dilutes it to 1,000 milliliters. What is the concentration of NaCl in the new solution? So this is what I'm talking about. I start with a 0.4 molar solution and I'm diluting it to 1,000 milliliters. So this would be considered the concentrated molarity, the concentrated molarity and the concentrated volume. This one right here is the diluted volume, and I'm looking for the diluted molarity. So I would do 0.4 times 50 equals MD times 1,000. And then you solve. So then all of a sudden this becomes a lot easier, hopefully. So the new molarity will be 0.02 molar, which makes sense. We should see that molarity drop quite a bit. You're making it less concentrated. All right, I think that's pretty much it. Oh, I got one more for you. Let's do this one. A chemist wants to make 500 milliliters of 0.05 molar HCl by diluting a 6 molar HCl. The molarity ones are easy to figure out because obviously the higher molarity is the more concentrated. So if I'm doing again, MCVC equals MDVD. This is 6 times the missing volume equals 0.05 times 500. And then I can solve 0.05 times 500 divided by 6. Yeah, I'm not going to need very much. Did I do that right? Sorry. 500 times 0.05 divided by 6. There you go. 4.17 milliliters is all I would need. And so what I would actually do, just to explain this part, is I would actually fill up this beaker with 495.83 milliliters of water, and then I would add this last little bit in so that I'm up to 500 milliliters. So that is the idea for our dilution problems, and we'll go from there. All right.